Okay, in this video we are going to look at the area of triangles and sectors. Sectors as in a portion of a circle. We are going to look at two formulas for triangles. One that involves an included angle within between two sides, and then we're going to look at an area formula that involves just the sides of a triangle, known as Heron's formula. After that, we'll look at arc length, which is hopefully a little bit of a review from geometry, and then with that we will establish a sector area. And with these topics, I have a just abundance of really cool math problems that I'll have you guys look at. Check out this content in the Larson textbook, 488 to 503, if you want a second perspective. But let's go ahead and jump into the first formula for a triangle. So, we will start with an example. Find the area of triangle ABC. A reminder that the area of a triangle is half the base times the height. That is the formula that you were most likely introduced to in geometry. Notice here that we do not have the height. So go ahead and take a second to try to solve for the area of this triangle given two sides and an included angle. This is a side, angle, side pattern. All right, so if we want the height, let's find it. Right, this is what we call dropping in altitude. I guess I lifted in altitude, but start at B, make its way to the other side at a perpendicular angle. We want this height, and I believe we have everything we need because we have 33 degrees here, and we have the hypotenuse of a right triangle. So the height here is going to be, or I guess I should backtrack. Let me get this whole formula going. The sine of 33 degrees is the height over 12.2, right? And then in solving this, multiplying both sides by 12.2, we are going to get that the height is 6.645 units. All right, and now I have everything I need to find the area of this triangle. I have the base, I have the height, and I have 1/2. The area of this triangle, of triangle ABC, is 1/2, base 11.4, and then height, we just established 6.645, rounded to the closest 1,000th place, and that ends up being the area of this triangle is 37.874. That's just from calculating this. Units squared, or U squared. We don't have any units in this problem. All right, we just found the area of a triangle given two sides and an included angle. Let's do that in general. The area of this triangle, let's call it ABC. So this is going to be angle A, which means this will be A. We'll call this one B, which means the opposite side will be B. This will be C. All right, what is the area of this triangle? Let's go ahead and assume that we are given angle A, side B, and side C. So I'm going to go ahead and underline those things. Blue is what we're given. We don't actually know this. Angle B, side A, and angle C. All right, so what do we need? We need the height. What is the height? Well, we have A, so sine of A is equal to the thing we want, the height over another thing that we have, side C. Moving things around a little bit, we're going to get H is equal to C sine A. Cool, that's the height. We are given B. All right, so the area of a triangle, given side, angle, side, is 1/2 B C sine A. All right, what is this? This is the angle that we were given and the two adjacent sides to that angle that we were given. If you were given side, angle, side, the area of a triangle is very, very close. All right, cool. That's our little warm-up. If you want to go ahead and use that in a practice problem, you can go ahead. But I want to jump to the much more annoying side, side, side formula. what I want you to do is I want you to find the area of a triangle given one of the sides is 9 units, another side is 12 units, and the third side is 18 units. And this is actually where I say, go. Once you have attempted it, you can go ahead and skip to where the answer is. Or you can follow along with me here. So I'm going to go ahead and do this. I know that the formula for the area of a triangle is 1/2 AB sine C, all right, given an angle and the two adjacent sides. I know this is a little bit different than what I had before, all right, but you can plug in any angle and its two adjacent sides, whatever you're given, right? So I need side C, or I could go for angle C or angle B or angle A and then use the corresponding adjacent sides. I'm going to go for C. So I have 3 sides. What do I do when I have 3 sides of a triangle? I use the law of cosines. So I want angle C, cosine C, and then I know that the law of cosines is the side opposite the angle that I want. And then I'm going to have an a squared plus b squared. It's basically the Pythagorean theorem, but with this compensation here. Minus 2ab cosine c. And I have most of these things. Right? I have all of the lowercase letters. I just don't have the capital letter. Right? I'm going to do a little bit of finagling, and you can go ahead and do this too. But c, the measure of angle c, is the arc cosine of a squared plus b squared minus c squared, all divided by 2ab. This is just if you manipulate this so that you only have c. Oh, and by the way, I know whatever angle I get will be the correct angle. I know I'm dealing with an arc function here, and that generally leads to some confusion. But I know whatever angle I get here will be correct because I'm dealing with the arc cosine, which is between 0 and 180 degrees, its output. So I will get a triangle's angle, right? And this ends up being, when you plug in 9, 12, and 18, right, the arc, right, C is equal to the arc cosine of, we have 9 squared plus 12 squared minus 18 squared all over 2 times 9 times 18, and that is, plugging that into a calculator. Ooh, wait, that should be a, by the way, that should be a 12. I realized that as I was using the calculator. And that ends up being 117 degrees. I'm going to plug what's exactly in my calculator. This is just the rounded degree. And so, with that said, let's go ahead and plug that into the area formula, 1/2 AB sine C. Which in this case is 1/2 9 times 12 times the sine of 117 degrees, which ends up being 47.994. But this is not the best way to do this problem. The best way to do this problem that we just did is to use a different formula. I'm going to go ahead and label this triangle. Right? We are not given the angles, but we are given the sides. Right? And it's something called Heron's formula. And we're going to derive what that thing is. And it uses something called the semi-perimeter, which we're going to denote with S. The semi-perimeter. And the semi-perimeter is 1/2 the perimeter, a plus b plus c. So we're going to utilize this number to determine the area of this triangle. And then follow along with me in order to prove this new formula. The first thing we're going to use when we prove this formula is what we derived in the previous problem, and that is, given a, b, and c, angle c, let me change it up, angle c with orange is the arc cosine of a squared plus b squared minus c squared all over 2ab, right? This is just a different form of the law of cosines, right? This is the measure of angle C is the arc cosine of a squared plus b squared minus c squared divided by 2ab. All right, but in addition to this formula, this law of cosines formula here, we're going to use your favorite identity, sine c squared plus cosine c squared is equal to 1. I bet you did not see this formula coming back anytime soon. All right. The way we're going to use this, though, is using the fact that cosine of the arc cosine of an angle is equal to that angle. How are we going to use this? We're going to plug this thing into C. Here we go. We have sine squared of C plus cosine squared of C, but C is the arc cosine of A squared plus B squared, so on and so forth. So I am going to just plug that thing on in. A squared plus B squared minus C squared, all divided by 2AB, and that is equal to 1. I'm going to take this thing to the next page. Why is this thing useful? Because let's solve for sine C. So sine C is equal to, I'm going to move this thing over, 1 minus, right, sine squared C is equal to 1 minus. I'm going to take the square root of both sides. All right, 1 minus A squared plus B squared minus C squared all over 2AB. Ooh, this is squared. I realized I didn't write that on the previous page. Let me jump back. This should be squared, right? Because this thing's squared. Right? We have sine C. And guess what? The area of a triangle is 1/2 A, which we're given, B sine C. This is what we call Heron's formula, named after the hero of Alexandria, hence Heron's formula. But it gets much better because earlier I talked about this thing called the semi-perimeter, and we are going to find the semi-perimeter in this madness. Let's do a little bit of cleaning up. I encourage you to do this derivation. I think it's totally in your wheelhouse. But as I go, I'll just exemplify some things that we often do when simplifying so that you can utilize them. And feel free to pause every time I say something and then try to finish. Finish right now, or get to that point where you think you can then finish. What I'm going to do, a very common thing that we do is we find a common denominator within the radical. So that's what I'm going to do here. I have this 1/2 AB, which I'll deal with later. But I'm going to, right now, get a common denominator. So 1 is 2AB over 2AB. So I'm going to go ahead and write 2AB over 2AB. But I also want the square here, so I'm going to square this thing. Right, that's still a 1. Right, A squared plus B squared minus C squared all over 2AB. And this whole thing is squared. Right, so we now have a common denominator. I can combine these two terms. So I'm going to go ahead and do that. Right, these have the same denominator, 2AB squared. Right, and the numerators are 2AB squared minus, and the numerator over here is A squared plus B squared minus C squared, all squared. All right, sweet. So we have 1/2 AB times this big mess. But we're getting somewhere. All right, if you see something, go ahead, pause the video, and try to get to the end on your own. The next thing I want to point out is we have, let me put parentheses here. We have a 2AB here. right? And 2ab, a squared, b squared, that is potentially a perfect square trinomial, a squared plus 2ab plus b squared. So maybe we can do some factoring somehow, right? Use that information to proceed. I am going to first pull out this 2ab squared. I don't like it there. It's messy. And since it's squared, I can just go ahead and remind a squared, square root of a squared, that's the absolute value of a. And since 2a and b are all positive, I can just go ahead and pull that thing out. All right, so I'm going to have ab over 2. And then if I pull this out, I'm going to have a 1 over 2ab, no longer squared because I'm pulling it out of the square root. And the ab's are going to cancel. That's really nice. And I'm going to have no more denominator in this radical. So getting a lot of good stuff out of pulling out that 2ab. Those go away, and on the next page, I'm going to have a 1/4 square root. Let me go ahead and make a better square root. Square root of 2ab squared minus this thing. Cool. All right. And then here is the sneaky trick. All right. I have a quantity squared and another quantity squared. I am going to difference of squares. I'm factoring those things. I'm going to have a 2ab plus the first thing. And I'm going to have a 2ab minus a squared plus b squared minus c squared. I'm being careful with my parentheses here because I don't want to get any sign errors, S-I-G-N. All right, did you even think this was about to be a big factoring problem? Probably not. All right, and then we got some more factoring here. All right, because here I can rewrite a squared plus 2ab plus b squared as a plus b squared. And then I have a minus c squared. Right, this is my first term. A plus b squared gives me those things, and then I'm left with a minus c squared. There's some more factoring to happen here. I have another difference of squares problems. Over here, I have to be a little bit more careful, but I'm going to have a positive c squared minus a plus b squared. All right, you can double check, but I'm going to have an a squared plus 2ab plus b squared. But then, oh, sorry, I made a mistake here. Saying that out loud helped. This is going to be a minus b. Because I'm going to have an a squared plus b squared from this thing, but I'm going to have a minus a squared and a b squared. I'm going to have a minus 2ab from this squared binomial, but this minus will make that minus a positive. All right, I know I'm getting a little bit confusing here, but stay with me. And then the c squared, the negative c squared is a positive c squared. Awesome. I'm going to do some more factoring. All right, I'm going to have, I'm running out of room here, a plus b minus c times a plus b plus c. All right, another difference of squares. And then over here, I'm going to have a c minus a minus b and a c plus a minus b. Boom. There we go. We are getting closer and closer to that semi-perimeter. I've gone and brought that last line on the previous page to this page. And I'm going to, despite the fact that I pulled out the denominator earlier, I'm going to bring the fraction out here back into the square root. What does that mean? I'm going to have a 16 on the bottom, right? Because the square root of 16 is 1/4. So I know I'm going all the way back to having a denominator, but there's a reason why. I'm going to have a 16 here. I have an a plus b minus c. I have an a plus b plus c. I'm going to rewrite this as C plus B minus A. Better yet, I'm going to write, I just like alphabetical order, B plus C minus A. And then last but not least, I'm going to have an A plus C minus B. We are really close to this final formula, right? Because this is really close to the semi-perimeter. Like if I had a plus C here, then I'd be golden. And you know what? I'm going to do that to every single one of these, right? I'm going to go A plus B plus C minus C minus C. I know it's a little bit confusing. But I have an A, I have a B, I have a 0, and then I have a minus C. So these are equivalent, right? And then I'm going to have an A plus B plus C. All right, that's the perimeter. I want that there. Here I want an A, so I'm going to have an A plus B plus C minus A. I've introduced an A. I have to get rid of it. And then I have a minus A. And then this last one, I'm going to have an A, and I want to introduce a B. So I need to get rid of the B that I introduced, minus the B that's been there the whole time. All right, and this is all divided by 16. But here's the trick. I can take this 16 and write it as 2 times 2 times 2 times 2. 2 to the 4th is 16. And then I can be even more clever. I can write this as 2 times 2 times 2 times 2. Just space them out a little bit. Right? And then I can be even more clever. I can just write this as 4 different fractions. Divided by 2, divided by 2, divided by 2, divided by 2. And I'm so close. This first term here, I have A plus B plus C divided by 2. That's the semi-perimeter. And then I have a minus 2C divided by 2. That's just minus C. This second term, I have A plus B plus C divided by 2. That's just the semi-perimeter. Right. Here I have A plus B plus C. That's the semi-perimeter divided by 2. And then I have a minus 2A divided by 2. That's just minus A. And then I have a A plus B plus C minus 2B divided by 2. That's the semi-perimeter minus B. Right? There is a really convenient formula. And I'm writing it down here. The area of a triangle given side, side, side is equal to the square root. Let me write this real nice. The semi-perimeter times the semi-perimeter minus A times the semi-perimeter minus B times the semi-perimeter minus C. This intense use of factoring has given us a really nice, really concise formula for the area of a triangle given its sides, and all you have to do is know the semi-perimeter and the sides. But you know the semi-perimeter because you know the sides. Let's jump back to this problem. 9, 12, 18. Given 9, given 12, given 18. The answer ended up being 47.994, right? New problem. Or the same problem, sorry. 9, 12, 18. All right, what is the semi-perimeter? That's half of the perimeter. So 18 plus 12, that's going to be 30. And then plus 9, that's 39. So 39 divided by 2, that's just shy of 20. That is 20.5. Sorry, it's just shy. 19.5. All right, so the area of this triangle is the square root of 19.5 times 19.5 times, minus A. So 19.5 minus 9, 19.5 minus 12, and 19.5 minus 18. And we're pretty much done. That is, once again, 19.5. This is going to be 10.5. This is going to be 7.5. And this is going to be 1.5. And the product, and then square rooted, is 47.994 units squared. And there you have it. That is Heron's formula. This is Heron's formula for the area of a triangle. So now would be a good time to take a break if you need it. I'm going to be jumping into the last portion of this video, the area of a sector, a portion of a circle. To do that, I want to look at arc length first. This is potentially, or hopefully at least, some review from your geometry class. But I want to know the length of this arc CD. I want to know this length, not the angle measure of this arc, which is a totally reasonable question to answer. Right? That actual angle is going to be 135 degrees because the central angle and the arc span are the same. But I want to figure out the length of this blue arc. And it's actually quite a simple task because conveniently, the ratio of the angle that spans this arc and the total angle in a circle, 360, the ratio between those two numbers, 135 and 360, that ratio is going to be the same ratio of this length. Right? These two measures are going to be the same as the length of the arc of CD and the total circumference. So the circumference of the circle. I'm just going to write C for circumference. Doing a little bit of algebra, we can quickly find out that the circumference 2 pi r, so the r is 10 centimeters, 2 pi r would be 20 pi. That is going to be, that times 135 over 360 is going to be your arc length. What is that number? CD ends up being 15 pi over 2 centimeters. What is arc length in general? Well, that is going to be the angle that you're given divided by the total angle in the circle, which is either 2 pi or 360, depending on the unit that you're working with. So let's go ahead and do 360. Actually, you know what I can do? I can do, this is for degrees. And I'll do the second one down here for radians. Okay, so theta divided by 2 pi. And that's going to be equal to that ratio, which is the circumference. All right, so 2 pi r. And the length that you want, A, B. All right, so the same thing down here. Oh, so I actually probably should rewind. Oh, no, I shouldn't. This is going to be 2 pi r, and this is going to be AB. Cool. So manipulating these, the two formulas are, for degrees, theta over 180 pi r, and for radians, just r theta. So the one on the right is a little bit nicer, but it just depends on the units that you're working with. Similarly, if you want to find the area of this space contained by the arc CD, the sector area, to be specific, the process is going to be very similar. All right, it's going to be the ratio between the angle and the circle, and is going to be equal to the area of the sector to the total area. So in this case, in the previous example, we have 135 to 360. Is going to be equal to the sector area that we want divided by the total area, which in this case is about to do circumference again, pi r squared. All right, so what does this end up being? This ends up being a little bit of algebra, gets us 75 over 2 pi centimeters squared. If we decide to do this in general, we're just going to have that angle theta divided by 360, or if in radians, divided by 2 pi, and that ratio is going to be equal to the area of the sector divided by 2 pi the radius, 2 pi r. And doing a little bit of Oh, sorry. Rewind. I keep doing that. Circumference. I want pi r squared and pi r squared. Sorry about that. And then if we do a little bit of algebra, you will find out that the final answer for these in general, 4 degrees, theta pi r squared over 360, and in radians, the simple theta r squared over 2. Once again, it just depends on the units you are given. So there you go. I just wanted to cover those two things really quickly because now we can merge the two things, area of triangles and area of sectors, and get some really cool problems going. So that you'll find those in the problem set that goes along with this lesson. All right, just to recap real quick, what did we do? We looked at two formulas for the area of a triangle, one where you have an inclusive angle and one where you have no angles at all. Then we looked at arc length and sector area, and then these are going to be combined to get some really cool problems. So I'll close it out here. Have fun with the problem set.